Thank you for coming and have a fun FOSDEM.
So, does the microphone work? Yes? Yes? No? This one? Great. All right. I'm going to talk about the embedded controller on Google's Chromebooks today and how you can use them in your own projects. Now, you might have seen I work for National Instruments. I don't work for Google. And you might be like, why does this guy talk about that? In my team, we build software-defined radios, so they use RPs. There's an entire track at FOSDEM on software radio, people using the radio to do that. And I kind of do the embedded part for our embedded products. It's a very small team within National Instruments, so we're kind of the open source weirdos. But I try to work upstream, and the way I ended up with this talk basically was we had the previous product, and it had a microcontroller, and it was an A-Tiny, and it was miserable because you couldn't update the firmware really well. And then I was like, let's not put microcontrollers anymore on our products if we don't need to. And well, then my hardware designer shows up and he's like, hey, we're going to put a microcontroller in the next product. And I'm like, oh, no. So I do what everyone does that does open source, right? You're lazy. You look around and you see, can you find open source projects doing your work for you? So sort of how I ended up here. I looked around, I found like Chromebooks. It was totally random. I ran into that they have an embedded controller firmware that's open source. So about Chromebooks, well, they're not so special. They're like just laptops, basically. Sorry for the marketing slides, but it's just an x86 or an ARM v7 or ARM v8 lately. It runs Linux, which is great because you can also run normal Linux in it. You don't need to use Chrome OS. They have a userland which is somewhat derived from Gen 2. Like long time ago, they forked it and did their own thing. And it's basically a very small laptop like that one, like super lightweight and everything. That has lots of battery life and also an embedded controller. So if you take them apart, that's a PCB of one of the older ones. It's an Asus, and it has a Celeron Braswell, and it also has an embedded controller from Microchip, and you can see in green. And that's hooked up via LPC, and you can actually buy that microcontroller. So I was intrigued. I'm like, something I can buy that runs software that I can find on the internet. Awesome. I can probably use that. Another one that's like the big brother of this one has a ROC chip in there. A bit more RAM than that one, and also has a microcontroller. In this case, it's hooked up via SPI. So fun fact, if you look at it, the actual SoC is down here and the microcontroller is over here. So if you compare the size of the microcontroller with the size of the application processor, it's pretty interesting, I find. Anyway, so let's look a bit about this firmware that I've been talking about. Well, it's 3-class BSD, which is nice. I mean, could be worse. It currently supports a bunch of MCUs that you can readily buy. They're usually M0s, M3s, M4s. So for my project, I picked the M0 because it's the cheapest one. There's kind of odd architectures they support. So from what I figured out, the way Google sort of does the whole Chromebook thing is they build reference boards. And then vendors like Hisense, like that one, or Asus goes ahead and takes that reference board and changes them around a little bit and turns that into a Chromebook. So often you have firmware that's the same for all of the Chromebooks of the Veyron series, which would be that one, for example. Woo! I already learned last year I had dark slides that didn't work, so I changed that to be white. Anyway, and they also say you should use kernel coding style, which is bonus points in my book because you don't get eye cancer like from a lot of embedded firmware. So yeah, you can just check out the code. It's on their website, and there's like zero documentation, so that's kind of the downside of the whole thing, which is why I figured having this talk is actually quite useful. There's one more talk that one of the Google guys gave about the subject at their firmware summit, but that's from 2014, so pretty outdated. So if you look at the source, you basically have a board directory where you have board-specific code. So a board would be a single Chromebook. You have chip where you basically find stuff that's for each individual type of microcontroller. So they support STM32s, they support the other architectures, and there's code like that does I2C for this series. So that all goes into chip. Then there's common, which is framework code where you have one level above that to do I2C. So if you want to do an I2C write or read, that would be in there. Or if you want to do a SPI transaction, that code would be in there. Or dealing with commands that the host CPU sends to the microcontroller over SPI or I2C or whatever the bus is, that would be in there. GPIO code. And if you look at core, you have like the OS code, a scheduler, which is, by the way, broken if you use GCC newer than 4.8, but I was willing to even accept that. So in driver, you have a bunch of drivers. They don't seem to have a real device model, so there's room for improvement, I would say, but it works. In power, you have power sequencing code for different SoC classes. So if you look at how you turn on an x86, or if you look at how you turn on a ROC chip, that always kind of works the same independent of your board. And so they have their own power sequencing for each SoC class in there. Include is self-explanatory, and in utils you have utilities like EC tool. They have a whole bunch of test and debug tools they made. So since the boards you can use that on are pretty cheap and often have USB, you can also use them to do something like USB to SPI or USB to I2C, and they have tools in there that do that. So those would fall in there. There's also an extra directory that I didn't put on the list because it has obscure things in there. And in tests, you find the unit tests. So to configure your firmware image that you're actually building, it's just an include file header that you just modify, and you say config blah blah. I want kind of like kconfig minus the menu. So each board, under the board, then the board name, let's say Jerry, because that's my Chromebook here. And then you have a header that configures which config options you're building into your firmware image, and the data structures and that you might also have in header get initialized and start up in the board file. So once you're done actually configuring, if you build it, that's one of the features that made it really interesting for me, because I had a bad time with firmware updates last time around with our old product. Is it already has a firmware update mechanism built in, and it's designed in a way that you have a read-only and a read-write image. In their case, it's mostly for security. In my case, it's really because I want to do field upgrades. So in the read-only image, you always boot into that, and then the application processor, like your ROC chip or your Celeron or whatever, will ask and be like, okay, what's your hash, like what kind of firmware are you running? And then the microcontroller will reply and say, okay, I'm running this version, and the host computer will be, oh, you should be running that version, and then override the read-write part if it's not what it's supposed to be, and then the microcontroller will jump into the second firmware image, and that happens on every boot. So like this, it's really neat because you always have new firmware synchronized with your kernel. So in my case, I just stick it into a flattened FIT file with uboot, and just in uboot do that versus what Chromebooks do. And they also use a GPIO pin. So to figure out whether you can overwrite that read-only image at the factory, they have just a GPIO pin. In some Chromebooks, that's literally just a screw that you can screw out, and then you're in hacker mode or something. And so I duplicated that also for my design because I felt that's pretty neat if you just have a switch, and then you can do factory initialization, so you avoid the whole hassle with having to have pre-programmed parts so manufacturing is happy. You just program it there. Yeah. So what do you get in terms of like as a programmer? Well, Chromium EC has tasks that have individual stacks, and they switch between them with interrupts. They have priorities, mutexes, timers, events, so it actually feels pretty high level writing code for it. Only caveat is you don't have a heap, so you can't malloc and free, but well, that's okay, I guess. So to define the task, you have Chromium EC has a bunch of files that get parsed by the build system and turned into something else. So in that case, you have the ec.task list, which is again board specific. And you have a bunch of tasks, and it's really easy to define your own tasks. So you have basically the function you want to call, and then a bunch of parameters. You say, okay, how big is my stack that I want? So some tasks just blink an LED or something, so you can have a pretty small stack. Others need more stack because they actually do stuff. So we had tasks. Then there's this concept of modules, which is not really the same as like you'd expect from the kernel, but it's basically things that need to keep state, need to get initialized on boot. Those go into what they call modules, and they're self-contained. On startup, they have an init function that gets called, sets up the state machine, and you know, like I2C, where it's like you have a bunch of registers you need to write just so the SOC is set up, and will do I2C, or for SPI, or if you have a bunch of ADC channels, which they have, if you want to monitor voltages, for example, then that gets set up when you have this module init function. Hooks is a pretty neat feature. So it's basically a callback. So you can say if a certain event happens, call this, or basically the opposite. You can say if a certain event happens, tell me that it happens and call this function. So for SPI, that would be if the application processor goes to suspend, stop listening to SPI commands because you're going to get garbage if any. So stuff like, oh, someone opened the lid, so maybe I should actually start turning on the LED to indicate my charge state, those kind of things. You can stick all that in a hook, and basically to declare a hook, it's very easy to say, oh, this is my hook name, this is the function, and this is the priority. So you can also have priorities and say, this one has higher priority than another. So using hooks and tasks, it's really, really convenient to do things like debouncing buttons. You just say, oh, on that event, call a deferred hook and see if it's still pressed. So you don't, since you have like timers and all this going on in the background, it's really a neat high-level way to deal with these kind of issues. So the hooks execute in the stack of the calling task, which is recipe for deadlocks, but I didn't look too much at the design, why they made the choice, but it's pointed out throughout the code that this is an issue. And they all get handled in a special hooks task. So if we go back, you see here is a hook task, the first one, that handles all these things. You have a console, so you can do stuff like printf. You can show, like you can select which level of debug you want by a concept they call channels, where you basically define a channel and then you just turn them on or off if you actually want to print them. It's really, really useful for board bring up. So my hardware engineer loves me for it, because you can just go in, log in over UART and say, turn on that power supply, turn on that power supply. Is the power good? Is it not good? And you can print out if so. It's really nice to have. You can also add custom commands. So if you have, say, you're getting more confident with your power sequence, then you can just throw it into a function, create a command, and just then call it from the console when all the rest of your debug setup is ready. Another neat thing is if you look at the prices of an FTDI chip and you look at the prices of a Cortex M0, if you just want to use the FTDI for USB to UART, then if you anyway put the microcontroller, you can just use the microcontroller's DMA capability to use one of the microcontroller's UARTs to just forward the serial console of your application processor, which is cheaper because you save an entire chip. Depending on the microcontroller you pick, you might not have enough UARTs or not enough DMA channels to actually do that, but well, yeah. Console commands, how to do it is pretty simple here. I removed most of what actually happens, but just to sort of give an impression of how you do it. So you say declare a console command, you say the name of the command. Behind the scenes, obviously, there's some magic happening with macros, right? Yeah, so let's talk a bit about how to communicate with the application processor. Again, that's like your rock chip, your Celeron, your Zinc, whatever. It's packet-based, so basically you stitch on a header and you have a checksum and data, and there's two versions of the protocol. Depending on the bus, obviously, since the buses behave a bit differently, I2C is different from SPI. It kind of, the lower levels are a bit different, but in the end, the protocol is the same. And what's also pretty awesome is like some ECs speak different versions of the protocol, and some even both. So version 2 kind of works like that. So you have a command with just 1 byte where probably if you think about it for 5 minutes, you already see why that's an issue. Then you have a command number, and you say, okay, you have that many parameters, you have the parameters, and then you have an 8-bit checksum in the end that always adds up to 0, if I remember correctly. So then you get back a response, which is a result code, again a byte, and you have a length, how long the result will be. You actually have the result, and so one of those commands could be read flash at that address, and then the length would say, oh, you read that much, and yeah, and then you have a checksum in the end. So there's also a version 3, which is, oh, can anyone guess why the version 2 was a bad idea? Going back?
Single byte command.
Yes. So, oh well. I mean, it's software, so you can update it, right? Nowadays it's more structured. Someone figured out, hey, how cool is that? Now you have like 16 bits of a number of commands that you can encode. That's a whole lot more than 255. So you won't run out of commands that fast. On I2C, it's kind of interesting because you kind of have to wrap it with a mysterious header to make it work. So that really worked well in the kernel, and it totally didn't work in U-boot. So I fixed that. I mean, patches are on the mailing list, so that works now. Yeah, so you also have like this host commands that you actually call with these packets. So if you want to declare them, again, you have a macro to do that. So you come up with a number for the command. I haven't figured out what the official process is upstream to come up with those, but probably you just send a patch and see what happens. Then you point it to a function that's supposed to get called, and you have a version mask, so there can be versions of a command. So you can, for flash info, which tells you about the properties of the flash that's built in, it will tell you in the version 0 just the size and the array size and stuff like that, and the version 1 has additional parameters. So with that EC version mask in the bottom, you create a mask of supported versions that you can take for that command, and then there's another command that allows you to query for each command which versions are supported. So that's kind of more future-proof. So I talked a whole lot about firmware and how can you actually use that in your own design? Well, looking at your SoC or your processor, you have a bunch of requirements. There's not a lot, but you basically need something to talk to it. So that could be SPI, which is what most modern Chromebooks seem to do, that are not x86. You could use I2C, and you can use LPC. They all have their benefits and drawbacks. SPI is basically, the benefit is it's really fast. The downside is it requires a really decent SPI controller because of the way it works. So since the protocol, the way it works is the microcontroller gets an interrupt and saying, oh, the host wants to talk to me, and then it needs to immediately respond. So if you build hardware like in an FPGA, SPI is really easy. If you do it in software, not that much, because you need to have a real fast response. So the way it works, it will say like, yep, I got your command, everything's fine, it's in progress. And then the host computer keeps clocking out cycles until it gets a preamble byte. So the problem with that is that not every SPI controller can do that. So in my platform, I have a FIFO that's 16 bytes deep, and I need something like 800 bytes or something. So it just doesn't work really well on an operating system like Linux, where at one point the schedule will be like, oh, well, you spent like the last couple of 100 milliseconds doing SPI, so now it's someone else's turn. So in U-boot, it works perfect for my board. In SPI, in the kernel, I just couldn't make it work because my SPI controller sucks. That's what I tell myself.
Don't you just use DMA?
Well, if your SPI controller can do DMA, yeah, I was about to say, like, behind decent SPI controller, it's basically like have really deep FIFOs or have DMA, because, yeah, my SoC just doesn't do that. So, which is why I switched over to I2C. It requires an I2C controller that can do repeated start, which seems to be, hey, it's 2017, what, right? But apparently not every SPI controller can do that. The SPI controller on my SoC has a massive bug that you need to work around, but again, that's not Chromium EC's fault, that's just SoC vendors. The drawback, it's obviously slower. I mean, the SPI would run at 5 megahertz versus the I2C that does 400 kilohertz. Just the benefit is basically that the protocol becomes easier because the microcontroller can just say, hey, I'm not ready yet, and it's built into the transport basically. And then there's LPC, which is kind of, for me as an embedded person, odd, because I don't do a lot of x86, and like almost no SoC actually does it in the ARM space. So if you build x86 boards, that's probably a good choice. You need one IRQ, probably 1 or 2 more pins, depending, to indicate to the embedded controller whether. So the power one is basically like, oh, now you can turn me off, which you could also send as a command, but it's easier just with a GPIO, and then you have already a kernel driver where you can hook it up and everything becomes really easy if you have like these 3 GPIOs. Yeah, picking a microcontroller. So it sort of really depends on how much you want your embedded controller to do. So like in here, in that one, it's a really small microcontroller because it doesn't do so much. It does power sequencing. Yeah, so I mean, you always need either the SPI and the I2C. It has a really neat feature where you can tunnel I2C, so hardware designer love you for that because sometimes you're short on I2C buses and pins and can kind of do sort of port expansion or bridging also. So there's code that does that. You probably want to look for PWM if you have LEDs and you need breathing LEDs. And if you want to do fan control, it's also a good idea to have PWM. You want lots of GPIO and you want DMA channels, at least for the communication, SPI or I2C. Maybe you want USB. I personally really like the idea of having a bootloader that just works over USB so that my customers, which tend to hack our products pretty badly and like they can't break it because it's built in, so you can always recover the firmware. So that's so kind of, it really depends on how much you want your embedded controller to do. Me, I'm super cheap, obviously, because so I went with that one, which is like $10. And it gives you USB. It has an STM32 on it, which is pretty much the same microcontroller that you can find in here, except for it also does USB, which I like because you can program it over USB. So what we actually do in manufacturing is we'll just use the USB port and use DFU to flash the firmware once, and then we can use the firmware upgrade mechanism that I talked about before. It has DMA, it has I2C, it has SPI, and it's already supported, so there's code for that board already. So I figured that's a pretty good target to start with. And another neat hack that you can do with that, or hack, whatever, I mean, most of the STMs are actually pin compatible, so you can just desolder that one and take a bigger one and reuse the eval board if you're not a hardware designer like me. So that's what I did. I just took the cheapest one I could find for like $10 and soldered a bigger IC that you just get for free as a sample. So yeah, so then you probably want to look at the pin assignment and pin maxing when you're building a product. There's more or less 3 classes. So you have inputs and outputs, which are like strap pins. So if you make the same board but in 3 different versions, and you want to detect that in software, then like you want to run the same code on 3 different small varieties of hardware, then use strap pins. You have LEDs and the write protect thing that I talked about. So those are just input and outputs. You have interrupt sources like external resets or buttons or switches, or like the power good line of a power supply that you want to be notified if that goes away. So interrupts, and then you have alternate functions. So a lot of GPIOs, like on modern microcontrollers, can have like so many different functions. So you sort of, before you build the board, need to sit down and figure out which pin will do what. And going back to the board I suggested here, if anyone tries that and try to use the default configuration for the SPI, you need to change the solder bridge on the back of the board to make it work. So it took me a while to figure that one out. But so all of those happen in a file that's called gpio.inc in your board directory, and it gets transformed by the build, so it's sort of this meta syntax that gets parsed and transformed. So I have an example again. The first one is the write protect. They use this naming scheme where _L will be low active. So it's like write protect, it's pin B4, and it's an input. And the battery LED, which is pin B11, and it's an output. and I want it to on reset be high. And then the last one is special because it's the interrupt that goes from the embedded controller to your processor, and that's pin B9, you want to be low. So the API you then get in the firmware to work with that is get level and set level, which is pretty much expected. I mean, it's a GPIO. So interrupt sources look like that. So you declare them as GPIO int. So in that case, you have the chip select for the SPI. And then you say, oh, again, pin, and you say, which edge do I want to get an interrupt for? And then you hook it up to a handler. In that case, it's a SPI event. You have GPIO interrupts for AC present. You have flags. So you can say, oh, I want to enable to pull up or pull down, basically microcontroller stuff, but wrapped up in a very convenient way, I feel. Yeah, the alternate functions, it's also not very well documented, so I figured I make a slide. It depends on the architecture, obviously, because every microcontroller does it a bit differently. For the STM one, it looks like that. So you create a pin mask where the mask is basically all the. So the first one is like F0 would be would be 5, 6, 4, 5, 6, 7, and you just OR them together and get the mask. And the 0 is the alternate function for those pins to turn them over to the internal SPI logic. And then you have the same flags that apply to GPIOs where you can say low active, high active, and so on. Another thing that's kind of special a bit is some code in the core assumes certain GPIOs to be there, like the write protect. So if you don't have it, you just declare it unimplemented and it will magically generate a code that fakes it so it works. It's really useful sometimes also if you just need to try out stuff, you just create fake GPIOs. And yeah, so one case why I ran into is like there's generic LED code that just defines behavior. So we have two LEDs here. So there's a power LED and somewhere there's a charger LED. In my design, I just had one LED, but I didn't want to write new code. So you just say the LED for the battery is unimplemented, and the code will just run and not do anything for the battery LED. Power sequencing, which is one of the big reasons why you have the embedded controller in the first place. A lot of SoCs need certain sequence. They always look sort of like, oh, turn on the 5-volt rail, wait for X milliseconds, then turn on that one, wait for X milliseconds, then turn on those two together and wait till the power good comes up. And there's a bunch of examples for SoCs that are built into Chromebooks. But if you use it for your own project where you have, say, I don't know, a Zinc or an IMX6, then you just have to write your own power sequence. But they come with a pretty neat framework to do that. So basically what you need to do to support your board sequence is you implement a state machine. They use the ACPI naming for power states, so like G3 for physically off and S5 and S3. So it's just naming. You can just look it up. But you have power signals, which is core code again, where you can assign certain pins as interrupts to be handled by the core code as power signals. And then if you do that, then you can wait for signals. So the in P good AP further up in the code is you AND together a bunch of, you OR together a bunch of, no, you AND them together anyway. So basically you can say those following conditions have to be true, wait for it. And in that case, the power good for the AP is the one that says like, okay, my system on chip is on, please don't turn me off. And yeah, they have a bunch of really nice functions that make it very easy to write these state machines. So they're all in the power subdirectory. Interfacing peripherals. So yeah, there is reads and writes for I2C that are already like API-wise there. There's an I2C tunnel, which is kind of special. I talked about that before briefly, where you could make peripherals hanging off of the microcontroller's I2C available to the application processor by tunneling over the transport you have in between. So you can do I2C over I2C, or you can do I2C over SPI or LPC. And that might come in handy. In my case, I have an EEPROM hanging off of the microcontroller that contains serial numbers, MAC addresses, those kind of things. But since I don't want another useless chip, I can also use that to store configuration for the microcontroller, because in my case, we built like rack mount devices, and some people put them on their desk. So for them, the power button should be like, I press the power button, it turns on. The next guy will be like, well, I have 100 of them in a rack and I power them over PoE. And I don't want to go to each of them and press the power button. For me, it's like if I plug it in, it needs to turn on. So those kind of settings you can just store in the EEPROM. And then the microcontroller has access to it. And the host can also set those settings over the tunnel, and there's locking in between to make sure it doesn't go wrong. There's a SPI API for being an SPI master. So some of the embedded controllers use SPI flash, but you can also use it to talk to SPI devices, obviously. So there's a transaction call where you say data, transmit length, and pointer to receive data and receive length. So it's pretty high level. Can do the same in an asynchronous way, but then DMA is required. Yeah. So, I mean, personally, I really like working with upstream stuff. I don't want to bother with stupid, like, 5-year-old vendor kernels that are broken all the time. So Chromebooks use heavily patched, really old kernels, but from what I've seen in the commit logs, is they spend amazing amount of time and money to backport things for a product like that costs $80. And since by design they're basically Linux laptops, they usually work really well. And so the integration also in the kernel is already there and just works. So for me, often when I needed support for something in U-boot, I can just look at the kernel code and hack it up to work in U-boot. Most of the actual Chromebooks use their own bootloader instead of U-boot. So the actual U-boot code gets less flight time, let's say. There's little motivation to actually run U-boot on a real Chromebook. So when I started out trying stuff, it was just terribly broken, and like there's no way this ever ran on any hardware because it just didn't work. But so I talked to Simon, who's working on that in U-boot, and sent a bunch of patches, and now it's working really well. The one thing that's missing is this software synchronization that I talked about with the firmware on boot up. I have code that does that, but I'm still sort of trying to figure out how to do it in a way so it fits into the U-boot device model and works for Chromebooks and non-Chromebooks, because the Chromebooks have a certain way of describing their firmware images, and it's not what I want for my platform. So, but it needs to work for both. So I'm still working on that. I didn't look at adding verified boot. It's sort of beyond what my customers care about. So, talking about U-boot, talking about kernel, you always end up with a device tree. So instantiation is pretty obvious. For the I2C, you give it an address. You say, this is a Google I2C embedded controller. You need an interrupt parent, and it's a wake-up source. If you have a tunnel, then you have, if you tunnel I2C, then you'd have a bunch of subnodes still, but it's already well documented. For SPI, it looks pretty much the same, so I give it a chip select, in that case, the first one. And you say this is an SPI version of the Chromium EC, and your IRQ level is, in that case, low, and it's all documented in the kernel. What do you get in Linux to talk to it? Well, it's not really all that exciting. I mean, it's just a janitor, basically, right? So it's a MFD multifunction device, and the sub-devices that are right there in mainline at the moment, I think, is the I2C tunnel, which is just represented as a normal I2C bus in Linux. So Linux wouldn't even know it's tunneling through the embedded controller over SPI to talk I2C with it. PWM channels, I think, is pretty new. I think 4.9 maybe, no? I don't know, something like that. Battery, there's drivers for the light bar. A lot of that will just show up in sysfs under sys platform Chrome OS cross EC and then something. There's a character device that allows you to do ioctals. So there's EC tool that I'll talk about later a bit, which is for debug, really useful because you can rapidly prototype commands before you start and sit down and write kernel code, which arguably takes longer because you got to reboot. And most of the code in the kernel is actually in drivers MFD, cross EC, I2C SPI, and drivers platform Chrome, where all the protocol stuff, which is the same for all, lives. Yeah, in sysfs it basically looks like that. So the sys class, Chrome OS, and then you have power and you have flash info, which you can just cat and it will tell you this is a, I don't know, microchip MCU. It has that much flash, the array size is that size. And then there's EC tool. There's a lot of functionality already there, so you can like query GPIO states, you can query firmware versions, you can reboot the embedded controller, so you can do it like the whole jump between firmware A and B, or read only and read write. You can get flash info, you can read and write the firmware, so obviously you should make sure that only root can do that. You can send commands, and in general, it's really, really useful for development because as you keep adding your own commands, as you keep adding your functionality, you can, I mean, you write a bit of C code and you don't have to write kernel or U-boot code. In U-boot, it's also not very exciting what you get. It's just a miscellaneous device. It's integrated in the device model already. You also get the I2C tunnel, so it again just shows up as a separate bus. You can read and write the firmware. You can get flash info again. You can reboot the EC. So you can also jump back and forth in U-boot. So if you want to do like a super trivial, a super ghetto U-boot script software sync, you can do that also by just reading back the firmware on every boot and just doing a mem compare with what you have or what it should be, and if not, write it. So the functionality is all there, it just needs to be tied up in, yeah. The code is in the directory is there. So, I don't know, I'm super fast. Now, let's talk a bit about community because it's FOSDEM, and so it seems to me from observation no one ever talked about this, so I must be one of the few people that do that outside of Google. I mean, it's very not clear what's going to happen next because it's Google internal development. Every now and then there's like someone pushes stuff to Git and say, oh, something happened. And that being said, they're very receptive to patches. Like, I was amazed. You send like a day before Christmas, you send a patch using Garrett, which is annoying, but anyway, someone reviews it within like 3 days. So that was actually quite nice. And other than the kernel, you don't get yelled at for misspelling your commit messages. So there's a mailing list, I think. It's like, I don't have a link, but it's very low traffic. So I would say there's no real community, but I'm starting it. Yeah, I think that's all I had. So I think we still have a bit of time for questions. Yes. Well, I'm just going to repeat it so no one needs to run.
Callbacks run in the same stack as the thread that they interrupted.
Yes.
And I assume that if you set up a different priorities, they can also interrupt each other. Isn't that one of the reasons that a lot of time also like a shared state corruption and stack corruption right there? Because you get like 60% of the patterns that are much bigger stack because that one is equally valuable.
So the question was basically whether the hooks being called in the callbacks being called in the stack, and I have to in the same stack as the caller. Yeah. Anyway, short answer is I don't have an answer for that, but yes, it's probably bad. Which is
Seems like you could also run things like error nodes, but you're still in the same thread.
yes, probably. I mean, it's the tasks are very simple C code. So personally, I've tried to break it and I couldn't get to that point. So I think it's pretty annoying if you actually run into it and it happens and you don't know why, which is why I put it on the slides. But
You mentioned like code generation. Is it all macro metaprogramming or is there an external code generator that is like the build stuff?
so the question was whether the code generation that I talked about is macro meta programming or whether there's a code generator. I think it's literally just macros, which I guess is fine for firmware.